So let's look at electromagnetism. We've seen that the Maxwell equations with sources, in other words, curl of B proportional to the current density. What is that? Ampere's law, and divergence of the electric field proportional to the charge density, Gauss's law. They are included in this covariant divergence, where JA is the charge density and current 4 vector. So, right, if we take a divergence of JA, and we do that, then of course that means that we're doing the same to the other side. And right, so we evaluate it locally, so we look at a special relativistic version of this, and right, the right-hand side of this, we just get a conservation law that we're familiar with, so it's just dj0 with respect to t plus dj1 with respect to x plus dj2 with respect to y plus dj3 with respect to z. Right, I could have written x0, x1, x2, x3. And this is just a statement of, well, this is, let's see, we can write this as, we'll just write some constant. I don't know, let's put a d charge density, dt, plus divergence of the current density, and that's equal to 0, right? That's just charge conservation. And this side, of course, has to be 0, so we can show that. So grad A, grad B, FAB, that is in a local special relativistic frame, d by dxa, df, this is df a 0, so I'm summing on b, plus the f a1 x1 plus df a2 x2 plus df a3 x3, which is d by dx0 of df00 with respect to x0. I know that's 0 by itself, plus d by dx1, df10 with respect to x0. Plus, now I'm at dx0, df01 in x1 plus d by dx1, df11 in x1, df21 in x1 plus d by dx3, df31 in x1 plus d by dx0, df02, x2 plus x1, df12, and x2 plus d by dx2, df22, that by itself is 0, that by itself is 0, of course, d by dx2 plus d by dx3, df32 with respect to x2 plus one more line here, d by dx0, df03 and x3 plus by dx1, df13, x3, d by dx2, df23 and x3 plus d by dx3, and df33, that by itself is 0, of course. And what is this equal to? Well, where are we? Let's get a different color here. Let's get green. So this disappears by itself. This disappears by itself. Ft2 and F33. F10 is minus F01, so you have time and x derivatives here, so these two cancel each other out. Same thing is true here with this one. X0, X2. This one, F30 and F03. Same with that. And this one, where are we? F21 is an F12 here, X1, X2. They cancel out. 3, 1, and 1, 3. Right, this is an anti-symmetric tensor, and then there's a 3, 2, and 2, 3. And so the whole thing is equal to, in fact, 0. So we look at the structure, and we can sort of ask, can curved space-time be sourced in this way? So maybe we can write. So by analogy, we could think of writing, right, so we just explored the sources here leading to the fields in here by way of this covariant divergence. And so we could say, well, there's a tensor about curvature, the covariant derivative, the covariant divergence of which is equal to some constant sum times, say, the form momentum, where we can make a conservation law from this, energy and momentum, right? It's energy and momentum that will curve space-time. Perhaps it looks like this. So the thing to notice about this is that there's the first derivatives of the EM field are related to the source. So the first derivative of the EM field are directly related to the source. And therefore, right, we end up, to get the source, FAB, electric and magnetic field, you have to integrate charge and current. So if you remember, the electric field is just the integral of the charge, right, over all of space, wherever the charge density is. We integrate over all the charge to get the field, and for the magnetic field, it's similar. You have the Biot-Savart law, where if you have a line current, you have IDL cross R hat over R squared. You integrate over all of the current that's in space. Here you integrate over all the charge, wherever the charge is distributed. And so we would be saying something similar here. We would be integrating over all the energy and momentum to get the curvature. But this is a little strange because it would be like integrating over the field to get the field, right? Because here we have a field in space-time, whereas this is space-time itself. So this doesn't look like the right approach. And even if we insisted on this, we would have to, or because we want dPA with respect to XA to be equal to 0, a conservation law for energy and momentum, we would want a similar thing here for this curvature object. I just wrote it as G. Eventually we'll write the correct curvature object as G, but now we're just saying we're gonna start guessing at what this can be, and it would have to satisfy this property if this were the right approach. So it looks like this is not the right approach. We need a more direct connection between this curvature object, and now I'll write it like this because I'm not thinking about covariant divergences, and the object that's supposed to curve space-time. So that's energy momentum, but of course I can't say, let's put a constant, I can't put PA here because that's a 4 vector, and so I'm going to need some object that is constructed out of energy and momentum in some way that it's a tensor. So I'll just write the tensor as T, which is the correct notation, but we have to figure out what these two things are. So we know about the Ricci tensor, which is a second rank tensor. We know about the Ricci scalar. We can make something that's a rank 2 tensor that involves a Ricci scalar. We will sort of straightforwardly construct this kind of an object and see that this energy momentum tensor will in fact obey this conservation law. Will actually be richer than this kind of an object. And of course this means that we need to find an object that belongs here that satisfies that as well to be compatible with that conservation law or those conservation laws.